This is the solution to problem 4 from section 6.3 online homework. I'm going to do this one because, as I was saying in class, a lot of the problems that involve trig functions, in this section, the functions are going to get squared because of the cross-sectional area. And so we see the integral of trig functions squared a lot in this section. And this is something that you can do with substitution, but it's something that you first need to use a trig identity to change the problem, and then you use substitution. So let me show you an example of it. So here, this is a very simple problem. The region is shown on the screen, and what I'm going to do is pick a place for my x, my slice. So here's a slice. And the idea is that when I pull this slice out, it's going to look like a disc. Oh yeah, don't forget I should make sure you read the problem. We're rotating this around the x-axis. So, so the whole region is going to get rotated around the x-axis, which means in particular, this stick right here is going to get rotated around the x-axis. So when that happens, the center right there, the center of this disc is really lined up with this axis, and this radius, this stick, is rotating around that. So what that means is that this is a little disc with thickness. Remember, we call the thickness delta x. And the radius of this stick, boy, I'm having a hard time drawing on this thing. The radius of the stick is exactly the same as, the radius of the disc is really just the height of this stick. And the height of that stick is just the y-coordinate right there, and that y-coordinate is given by that equation. So after all of that, the volume of the slice is approximately pi times the radius squared. Well, here the radius is given by cosine 16x times the thickness. And so the volume of the whole solid in the limit is going to be the integral from 0 to pi over 32. I'm just reading this off the graph. I don't have... Oh, good God. There's not enough room to write it there. So the volume of the whole thing is the integral from 0 to pi over 32 times pi times cosine 16x squared dx. So that's usually the theory, and I apologize if that's a bit of a rush to get the setup, but I really want to talk about how to do this integral. They do give a hint here, and this should be a huge hint, because this is really the key to doing integrals of sine function or cosine function squared. Before I do that, though, I'm going to just say that this pi can go out here, and just don't forget about it. So there's a pi out in front of the whole problem, and we'll come back and make sure we don't forget to put that in. So the first thing is, other than making sure the pi is there, is to rewrite the cosine squared as 1/2 1 plus cosine of twice that angle. So it doesn't matter what angle this is, it's going to be 1/2 times 1 plus cosine of twice that angle. So, because here the angle is 16x, then this is going to be 1/2 times 1 plus cosine of 32x, of all things. And so that is a correct trig identity, that cosine of 16x squared is 1/2 times 1 plus cosine 32x. And it just comes from that guy. All right, well, now I have a half factor, and so I can move that outside. So let me just do that. Make this pi over 2 out here. Did not mean for that to be red, but okay. Make that pi over 2 and get rid of my half. And now I'm getting pretty close. This is pi over 2 times, I've got the integral from 0 to pi over 32 of 1 plus the integral from 0 to pi over 32 of cosine 32x. So the first integral is easy. The integral of 1 is easy. To deal with the cosine of 32x, I'll just use a simple substitution of u equals 32x, which means du is 32 dx. And so I'll have my pi over 2 still sitting there. I'll go ahead and do this integral. This will be antiderivative of 1 is x. Evaluated between these two values just gives me pi over 32. And then I have this integral to do by substitution. If you were to draw a picture of this, you would actually see something that simplifies this quite a bit, which is that going from 0 to the power of 32 gives you a negative and positive part of this curve that are identical. So I can tell from the symmetry, since I know what the graph looks like, I know that's going to be 0. But let's go ahead and do it with our u-substitution just so we can see it all works out. With a u-substitution, I'm going to have 1/32 times cosine of u du. And that's because this guy here is the same thing as 1/32 du equals dx. And when I make the substitution, don't forget that we have to also deal with the limits. So here x is 0, which means that u is 0. And here I have x is pi over 32, which means that u is pi. And this is where I was saying you can tell this is going to be 0. I'm integrating the cosine function from 0 to pi. And if you were to go look at a picture of the cosine function from 0 to pi, you can tell this is going to be 0. But let's just persist. The pi over 2 times pi over 32 is pi squared over 64. And then I'm going to have the pi over 2 is going to be times this guy, but this guy is going to be 1/32 sine of u evaluated from 0 to pi. And I could keep saying that is going to be 0. Sine of pi is 0, sine of 0 is 0. So the final answer here is just this pi squared over 64.